Maybe as a little placeholder, I should just have this up until I find my sheet. Yeah, over behind me. Come on over here and grab some. Okay. All right. Everybody who's not listening, at least be quiet so other people can listen. Um, Here's the drag equation, which I've never taught you, but you may just find it interesting and it may clarify some things. It should make sense. So the force of drag equals, and you don't have to write this down, you don't have to know it. I won't ever test you over it. It equals 1/2 times A. So A is the cross-sectional area. A is how big this person is. Now notice if you're falling like this and you're pushing against the air, you're going to have a bigger area pushing the air than if you fall like this. So if you're falling like this, it's just your area would be that. But if you're falling like this, your area would be that. So you'll fall faster if you fall like this than like that. It's like diving into the water. There's drag when you hit the water, and if you go in like a really good diver, you make very little splash, you're going to end up going deeper than if you do a belly flop. Belly flop, you've got a big area. So to calculate drag, you start with 1/2. I don't really know why. Multiply that by your area, and then you multiply that by a thing called the drag coefficient. I was just reading. Let me show you this. I don't know. It may take me a little while to get to, but it may be quick. BMW has made a really cool electric car. BMW electric. What's the word for really expensive car? Luxury car. Okay. And I bet they have it here. So this, I was reading about, I don't know which one it is. Maybe it's this one. A lot of people didn't like the look of it. Maybe, I think it's that. It's with the gull wings. I don't know. The BMW I's, they call it. But anyway, I was reading about this car right here, the i7, and it's really expensive. It's over $100,000 for the base model. But when I looked at that, does that look aerodynamic to you? But it turns out that the drag coefficient for this car is 0.24, which is really, really small for a car shape. And I'm not sure how they achieved that and still had it look like a car. But if you look at a Prius, it's not like this. And a Prius, I think the drag coefficient is higher than 0.24. Let's see. Yeah. So here, a Prius has the same drag coefficient as that. Now, does anybody know the shape with the lowest drag coefficient? If you wanted to make something really aerodynamic, so you could fall as fast as possible, what would the most aerodynamic shape be? Not a triangle. Um, it's not a cone. Nope. So think of something that falls from the sky and forms itself into the shape that will help us. Yes. Sort of a teardrop, or sometimes people call it an airfoil. So a teardrop, it says, is the most aerodynamic shape in nature. It's got a drag coefficient of 0.04. And if we looked at pictures, this is just showing how if you have, let me open this is a new tab. If you have a flat piece of plywood and this is the wind moving over it, it creates all this turbulence behind it and a lot of resistance. So the drag coefficient of this will be 1. And for a sphere, it's a little more aerodynamic, but not a whole lot better. The drag coefficient is about 0.5. For this, it's 15. If you make it a little thinner and elongate it, then it's like 0.05. So yeah, so has anybody ever seen cars that were designed to go, like, to set the record for the highest gas mileage? Let's see, world record most miles per gallon car. I think what we'll probably see here is, yeah. So there we go. There's a car that they've basically tried to turn into a teardrop shape so it would be really, really, really efficient. It's not, you can't take a lot of groceries in that. I'd say if you got in a head-on collision, it'd be kind of bad. But let's see what the record was. It's a Guinness record, 14,573 miles per gallon. But it's a fuel cell car, so I'm not sure exactly what that means. If it's a gallon of hydrogen turned into a liquid, that's not really a fair comparison. So back to my formula. So if you wanted somebody to fall fast, you would put a little teardrop shaped capsule around them. Then that would decrease the drag coefficient. So for a baseball, this would be like 1/2 times whatever the area pi r squared is of this baseball times 0.5, which is the drag coefficient, times this. I bet you've never seen that. The chemistry teachers, I don't know why they do it. They use D. So D is for density. This is the symbol for density. So if you're going through something really dense, there's more drag. Which would have more drag, water or air? If you tried to walk through air really fast and then you tried to walk through water really fast, which would be harder? Water, because it's got a much bigger density. Air is not very dense. And then the last thing, this is maybe the most important one for Gianni's question, is V squared. Guess what V is? You've seen V before. Velocity. So according to this, if let's just say your velocity is 20 miles per hour. So if you square 20, you get 400. And then let's say you speed up to 40 miles per hour. If you square 40, you get 1,600. So even though your speed is just doubled, the drag has quadrupled. So your speed has a big effect on drag. And that's why if you drive an electric car, or really any car, as you go faster and faster and faster, your fuel efficiency drops off really fast, because every time you increase velocity a little bit, the drag increases a lot because that velocity gets squared here. So as somebody falls, let's just use this person as an example. They're falling, their area is going to stay the same, their drag coefficient is going to stay the same, the air stays the same, but as they fall faster and faster and faster, the velocity of the air moving over them gets bigger, and that's what changes drag. So before reaching terminal velocity, your weight is going to pull you down with a certain force, but drag is going to be less than that. So that means you've got a net downward force, and you're going to keep speeding up, and that's going to make this drag grow because velocity is going to continue to grow. When you get to terminal velocity, your weight's still the same as it was before. These should be the same. But now your drag has gotten to be so big that it's the same as your weight. And when that happens, you have zero net force, so you don't change speed anymore. You don't go any faster, so drag stops changing. But then when you pull your parachute, now what have I changed in this formula? A, CD, density, or velocity by pulling the chute? Two things actually change. A is changing because this is bigger, so it's got more area. And also, do you think this is a more aerodynamic shape? Probably not. In fact, if you do a good parachute, this is a super non-aerodynamic shape. If you make a hemisphere like this and you try to push it this way into the wind, it's absolutely not aerodynamic. So the area goes up, the coefficient of drag goes up, so the drag goes way up like this. And your weight wouldn't be any different. So the weight in all three of these pictures should be exactly the same. But in this, you're accelerating upward. Does that mean you're moving upward? When people are parachuting and they pull the chute, do they start to move upward into the sky? Look at this diagram, do they? They don't actually go up, but they're moving downward. They have negative velocity, but a positive acceleration. So if you're moving downward and accelerating upward, what's happening to you? You're slowing down. So just like the first test, if somebody's got a negative velocity, meaning they're moving negatively, but they have positive acceleration, meaning they're being pushed up, they're just going to slow down in their negative movement. And as they slow down, what's going to happen to the force of drag if the velocity decreases? It's going to get smaller. So this arrow is going to shrink, 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 shrink until it's exactly this long again. And then they're just going to continue floating down. But they'll do it with a much bigger area and a much smaller velocity. So